What you see now in front of you is a standard laboratory potentiometer. Now you must be wondering that why does this thing look like an extended meter bridge? Well, the answer is that at least from the looks and the make of the structure, it does resemble a meter bridge, but it differs from it on many fronts. First, it is generally composed of 4 to 10 wires in series, each almost 1 meter in length. Second, its principle of operation is based on potential gradient, while that of a meter bridge is that of Wheatstone bridge. Third, though it is entirely possible for a meter bridge setup to function like a potentiometer, it will lack the sensitivity because a meter bridge generally has only a meter long wire, while a potentiometer may have 4 to 10 times that length, making it 4 to 10 times more sensitive. And finally, the major difference, though, is not the physical structure, but the underlying principle of working, which we will see in a while. A meter bridge works on the principle of a Wheatstone bridge, whereas a potentiometer works on the principle of potential gradient or potential drop per unit length of the wire. This we are going to understand more deeply in the next part. Now, let us try to understand why do we need a potentiometer at the first place. The answer is, you must be aware that every cell has an EMF and an internal resistance. Now the problem is, you cannot measure the EMF of a cell using a voltmeter or any such direct measuring device. The problem is that an EMF manifests only in an open circuit, which means that a cell should not be connected in a closed circuit, because if that happens, then current will be withdrawn from it and the internal resistance will kick in, which will create a potential drop, and the EMF will not be measured. As you can see in the diagram in front of you, there is the EMF, there is a cell with the internal resistance here, and then we have the current, we have this external resistance and the potential measuring device, the voltmeter basically. So we know that current can be measured or calculated as E, that is the EMF, upon R plus R, because these two are in series, which gives us that E equals I capital R plus I small r. This will lead to an equation that the potential difference measured here will be E minus IR. Now imagine, instead of this voltmeter here, if I place the voltmeter across these 2 points, will it be able to measure the EMF? Certainly not, because the voltmeter will have an external resistance, a resistance of its own, and hence the voltage that it will be measuring will never be the same as the EMF. This can be same under 2 conditions. One, if the current is 0, or if the resistance is 0. Now, since the resistance cannot be 0, hence the I or the current has to be 0. Hence, no direct measuring device can measure the EMF of a cell. Because the problem is, if you do not put a cell in a closed circuit, you cannot measure the EMF either. So how is it possible to put a cell in a closed circuit and yet not withdraw current from it? And herein enters the potentiometer. Because a potentiometer can be set up in a way such that it nullifies the potential difference and hence in a way stops the flow of the current in the closed circuit, thereby helping us measure the EMF and the internal resistance of the cell. So, now that we have understood why we require a potentiometer, let us now see how a potentiometer is generally set up and how it functions in principle. So this is a general diagram for a setup of a potentiometer in the laboratory environment. These lines here, these are the wires of the potentiometer that we have seen previously. The distance between A and B is the length of the wire L. And the principle on which it works, as I said, is the principle of potential gradient. That is potential difference per unit length of the wire, which we will define here with the help of the variable phi. Now let us say our potentiometer device has a total wire length L and the supply voltage is V. Thereafter, the potential drop across the length of the wire is phi equals V upon L. And for our sake of understanding, let us see how an EMF can be found out and how two cells EMF can be compared. Let us say we have two cells here with EMF E1 and EMF E2. Let us consider EMF E1. We have a galvanometer here which reaches the null point at a length L1. Now when we say the null point, it means that the galvanometer does not show any deflection, which means that there is absolutely no current flowing through the galvanometer. This is only possible when the potential difference due to this cell or the EMF here and the potential difference that has been created between this point A and the null point L1 have become same. And when that happens, we reach a situation where the EMFs have balanced out and hence there is no flow of current. And if there is no flow of current, as you remember, what happens? I equals 0, which means our V can now be equal to E, and hence we can measure the EMF, and the EMF here comes out to be phi times L, where phi is volt per unit length multiplied by the length of the point where we get the null point. So we have the EMF of the first cell as phi times L1 and the EMF of the second cell as phi times L2. Hence, if we want to compare two cells EMF, we get E1 upon E2 equals L1 upon L2. Now, the most important point is, at the null point, we imply, or it gets implied, that at both the points L1 and L2, no current is flowing through the galvanometer, as the potential difference across the lengths of the wire have nulled out the potential difference of the cells. And this is how we measure the EMF. So now I hope you understand why we require a potentiometer setup to measure the EMF. That is solely because of one reason, that the EMF of a cell cannot be measured if current is being withdrawn from the cell. And as you can see in the potentiometer setup, we can create a situation like this one where the potential differences have nulled out and hence no current is being withdrawn from the cell. In that situation, when no current is being withdrawn, the internal resistance will not kick in and we will be able to measure the EMF. So I hope now you understand why is a potentiometer such an important device and how we measure the EMF of a cell. In part 3, we are going to see how we measure the internal resistance of a cell using the potentiometer concept. Stay tuned. So now that we have learned how a potentiometer can be used, let us do the final thing, the measuring of an internal resistance. Now, we already know how a potentiometer can be set up, and this is the same setup except that we have only one cell here, fine, whose internal resistance we are supposed to find out. We have a resistance box and we have key along with a galvanometer. Now, in case 1, we keep the key open. So when we have an open key, the EMF will be measured as a length L1. That means the galvanometer will show a null point at a length L1. So we will have the EMF as 5 times L1. When the key is closed, the resistance box kicks in. And in that situation, we get the potential difference V as 5 times L2, because now we have the null point at a new length L2. If we divide the EMF by the voltage that we are going to find out now, we get E upon V equals L1 upon L2. We know EMF can be measured as, or can be written as, I times capital R plus small r, where capital R is the resistance of the resistance box here. So the capital R comes from here. And the V is I times R. So by placing or by substituting the E and the V here, we get rid of the I and we are left with R plus R upon R equals L1 upon L2. A simple algebraic solution gives us that the internal resistance can now be found out as capital R times L1 upon L2 minus 1. So this is a very simple procedure of how we can find out the internal resistance of any given cell using the potentiometer concept. So I hope now you have understood what is a potentiometer, why it is required, and how it can be used in the measurement of EMF, in the measurement or the comparison of EMFs, and in the measurement of internal resistance. Thank you.